Hi, everybody. Okay, hold on, there's a chat. Okay, good. Yeah, so I'm really, really sorry about what's going on here. Uh-oh. Pens. There we go. Okay. Yeah, I'm really, really sorry about not having the recording. I'm recording this lecture in general. Hopefully I remember the rest of the lectures, but feel free to remind me. I am going to give you guys a write-up. Which will contain lots of information. But in the meantime, yes, I'll give you a recap from last lecture. So first of all, let's be clear on what we're doing. So our approach is to pick a connection strength, pick some weights, W sub ij, and analyze behavior of the network. And we're generally going to consider, and so far, so we've mainly considered firing rate equations. And so our equations always look like this. The Ri dt, where R is firing rate, equals some nonlinearity of the sum on J of Wij, Rj. Sometimes we have external input minus Ri. So external input okay, so that's mainly our picture. So let me double check. Sometimes, yeah, usually I put a tau here, sometime constant. Okay, so this is really the set of equations we've been working on, mainly with some exceptions over the whole course. And what we're doing now is, and so what did we saw? We considered randomly connected networks. So randomly connected networks, which had surprisingly rich structure. And we considered Hopfield networks. Which were point attractors. And these are very useful for associative memory. Well, for associative memory, so you can recall part of a scene, and that will tell you the rest of the scene. They're also useful in general. If you want to remember things for a short period, you need some kind of point attractor. You need to hold information in your brain. And so this was past lectures. So now we're just going to say, okay, Hopfield networks, point attractors are good, but what about line attractors? So this lecture, so recent line attractor networks. okay? And line attractor networks are sort of a natural extension of point attractor networks. In point attractor networks, a single point in activity space is a stable fixed point of the dynamics. In line attractor networks, you have a whole line that's a fixed point. And so there are actually two ways to picture line attractor networks, and you should probably keep them both in your mind. If this is Ri versus index I, so remember we have, so this is a differential equation in high dimensions, and it has, let's say it has fixed points. Fixed points are points where the right-hand side is 0. So let's be clear about that. So fixed points I'll write it Ri star because it's a fixed point equals psi of the sum on J of Wij Rj star. So that's a fixed point. What I'm going to plot is Rj star versus index. And because neurons are discrete, so it might have, you know, it could have anything, but let's suppose it has some shape like this. Okay. So what this means is, you know, some neurons are firing at high rate, some are firing at low rate. And if you arrange them properly, they look like a hill of activity. So I don't actually want to put all these dots in all the time. So what I'm going to do is replace it by hill of activity, okay? So this basically means I've just taken, this is in the limit of a really, really large number of neurons, all these points can look like a line, okay? And so this could be a stable fixed point, but if you have a line attractor, then shifting the hill of activity is also a stable fixed point, okay? So you have a hill of activity that's also a fixed point of the dynamic and is shifted over. And you can imagine this would be super useful for all sorts of things, if nothing else for remembering analog variables like angle or well, color in 1D. Later on, we'll see we can have 2D hills of activity or 3D hills of activity, but you can now remember in some sense a continuous variable. So exactly where you are, so you can be you can basically be in an infinite number of places. You know, you can also be over here. So there are an infinite number of fixed points. Okay. And so this picture of a hill of activity is really, really useful way of thinking about this. But there's another way of thinking about this. So another way of thinking about line attractors and we're going to go back and forth between two. So it's a really good idea to have both of these in your brain. And this is activity space. So this might be R1, R2, R3. And of course, there are really a lot more than things. R's go up to infinity, go a very large number. And so the line attractor is basically all these are points. So your line attractor is now points in these space. So what I'm basically plotting is R star, okay, as a vector. And so this point here, for instance, might correspond to this hill of activity. And this point here might correspond to this hill of activity. And this point here might correspond to this hill of activity, okay? And it's really, really important to be able to go back and forth between these two things because they give a different kind of insights. And all they really say is, look at these fixed points R star, there are lots of them, infinite number, they lie on a line. Every point here is a solution to this equation, okay? So that's a general statement about line attractors. And what we saw last time is that so there's a certain weight matrix that actually naturally give you line attractors, and that's Wij goes to Wi minus j. And so our equation becomes tau Ri dot. Let's not use shorthand. Dri dt equals psi of the sum on j of Wi minus j, Rj minus Ri. And what we showed technically is that basically what this gives you is not exactly necessarily a line attractor, but it guarantees you have lots of points in the line attractor. You have basically n point attractors. So j equals 1 to n neurons. So what this tells you, there are n point attractors. But we can ignore that and think of this, n goes to infinity, we'll just take n go to infinity. So the whole line becomes effectively an attractor. Okay, so this is really the back of our mind. This is a bit of a side points, but so we'll pretend like there's an attractor. And we're going to let, so before we called the fixed point Ri star, so the Ri star goes to Fi of theta. So theta tells you the position on the attractor. So if you went back to our previous slide, so basically this is, you know, so you can think of the coordinate system theta along here. So this point would be small theta, so bigger theta, bigger theta, bigger theta, bigger theta. And the theta really just corresponds to, actually, let's go the other direction. For reasons I'll tell you in a second. So theta, the coordinate system theta, okay? And what we're thinking of is in some sense that this is a theta axis. Just think of this as a theta axis. Okay. It just measures position. Theta now corresponds, in this picture, theta corresponds to point on the line attractor. In this picture, theta corresponds to the position of the peak of the hill. So this would be small theta, and that's that point. This would be bigger theta, that's that point. And this would be bigger theta, that's this point. Okay. So conceptually, this is all kind of reasonably straightforward. Okay. And if you have a network where you've perfectly tuned the weights and there's no noise in the system, this is what happens, right? You get a nice fixed points, and the fixed point really just means that the fact that a fixed point is important. That means if you start over here, if you start here, you'll go toward the attractor, maybe at some angle, but you'll always end up on the attractor. That's what we mean by a fixed point. And once you're on the attractor, you don't move anymore. Okay. So that's a perfect line attractor. However, in real life, line attractors are never perfect. Okay. So what I mean by that is the equation so the real equation describing neurons is going to be something like tau ri dot, sorry, tau dri dt equals psi of the sum on j of wi minus j rj plus, let's say, the sum on j of vij, because, and this term comes from the fact that we haven't perfectly set the weights. We want them to be wi minus j, but they're going to be wi minus j plus vij. Okay, rj, and then we'll add in also some external input. Actually, let's call this hi minus ri. So this is vij is from imperfect weights. And I'm going to put an epsilon in front of here. And then hi is external input. Or maybe it's just noise, because this is a rate-based model. In fact, with real neurons, they're firing rates and they fluctuate. I'm going to put epsilon in here too. And we're going to assume we're close to a line attractor. Epsilon is much less than 1. Okay. And so what we want to do is analyze the behavior of this network when you have these terms here. So we know what happens when W is chosen perfectly. What about when things aren't quite perfect? In real networks, this is always going to happen. Okay, you have external input. You might actually, so 2 reasons. One, there's unavoidable imperfections. That's the noise, say. But also, you might want to use these terms to move along the attractor. So I'm going to come back to this, but if you go look at our attractor, so it's kind of nice for remembering analog variables, right? Different points could be some memory. It's also nice for integrating evidence. So remember, so this is actually, it's worth mentioning now. I'm going to mention it again. So neurons, well, actually, I'll come back to this later. Okay. So you actually might want to deliberately add external input, and I'll tell you why in a little while. Okay. So we now have a math problem. We're adding extra terms. We added extra terms, and we want to know what happens. What happens to R? There's extra terms are small, and whenever you see something small, you immediately know small variable or small parameter do perturbation theory. Which in our case really just means do a first order Taylor expansion. Okay, so this is what we're going to do. And for doing a first order Taylor expansion, when you have a line attractor, is actually much harder than when you just have point attractors. And in fact, I've been playing around with these kind of networks for well over a decade. And it was only last night that I figured out how to do it in a really simple way. So it's kind of non-trivial. And what I'm going to do first is, instead of thinking about line attractors, we'll just take a step back and do some math. How do we do perturbation theory in general when you have a dynamical system? Okay. So I'm going to actually write just a whole new set of variables. Suppose we have equation dz dt equals g of z. G is a vector of Z. And that's shorthand for dz idt equals gi, some function that depends on z1, z2, up to zn. Let's say we have n variables, okay? The vector notation, though, is super convenient. And so we assume it's a fixed point. There's a fixed point. Which is at z equals z naught. So g of z naught equals 0, which is shorthand for gi of z0, 1, z0, 2, z0, n equals 0 for all I, okay? And z naught is going to be an isolated fixed point, okay? This is a fixed point, not a fixed line, so life is really easy. And the question is, what happens near what happens when we modify G? Okay, so I'm going to call this G0. This is some function. Okay, so it's fixed points. And now we're going to consider the equation dz dt equals G0 of z plus epsilon G1 of z. Okay. So we've actually modified our function. This is exactly analogous to what we're going to do with our line attractor. We're going to modify, where'd it go? Wrong page. Here we are. We're going to modify our function. This would be equivalent to G0. We're going to add another term. Now, when we add this term, what happens? So we're going to do this first for a much simpler case of point attractors. Okay. And we're going to assume, of course, that epsilon is small. And epsilon is small. So what we're going to do is let z equal z naught plus delta z. Okay. So z naught is fixed. Our equation becomes d delta z dt equals G0 of z naught plus delta z plus epsilon G1 of z naught plus delta z. Okay. And we're going to let this term here, this is approximately equal to epsilon G1 of z naught. Okay. And that's because epsilon is small and delta z is small. So any correction is going to be multiplied by a small number. Let's actually make this a little more rigorous. We can write this term as G1 epsilon G1 of z naught. This is actually a vector. Plus delta z dot partial with respect to z naught G1. And there's also n plus epsilon. And now we have two small parameters. Epsilon is small and delta z is small. So we just ignore this term. So we just ignore. Oops, oh man, sorry. Delta z. So what we're doing is just ignore. For this term, though, we do want it to Taylor expand. So we write this as G0 of Z plus partial of G0 of Z naught. Actually, this is Z naught with respect to Z naught dot delta Z. Okay. And so when all is said and done, so remember G naught, this term, so this term is 0. Okay. And I'm going to actually be clear about this term in a second. So we now have only 2 terms on the right-hand side. One of them is our Taylor expanded term. And the other is our, basically, this function, this perturbation to our function, but evaluated at Z naught. Okay. And that's fine if you can, if epsilon is small and delta Z is small. Okay. If it's small enough, it's reasonable to throw that out. Okay, so I'm going to rewrite that in vector notation. So we have D tau. Write this in black. So we've thrown away the tau. We just have D. Oops. D delta Z dt equals a partial of G naught with respect to Z naught dot delta Z plus epsilon G1 of Z naught. Okay. Now this, so we can actually, in terms of indices, this is, we can think of this as D delta Zi dt equals a sum on J of partial of G naught I of Z naught with respect to Z naught J delta Zj plus epsilon G1 I of Z naught. Okay. And this quantity here is a Jacobian. So we're going to define this to be Jij. It depends on Z naught, but we're not always going to write that. So this term here is a sum on J of Jij delta Zj. So we're going to write it as, in vector notation, this is D delta Z dt equals J dot delta Z plus epsilon G1 of Z. And J naught actually depends on Z naught. But we're not going to write that. We're just going to write it J depends on Z naught. That's not a big deal. So if epsilon is small, this is our equation. So what it tells us is, so let's think about this. If epsilon were 0, right, delta Z would be 0, right? If the right-hand side is 0, that's we're looking for fixed points of this equation in some sense. Okay. And so not only are we looking for fixed points, we can actually look at all of dynamics, right? So we can write this as, so here's the most important thing you'll ever learn about linear algebra. So we're going to so this is linear algebra aside. So linear algebra, in a nutshell, all you need to know. Okay, so we'll define eigenvectors and eigenvalues. J dot Vk equals lambda k Vk. So this, I assume you've seen this in your classes. This is an eigenvector. This is an eigenvalue. And what they probably may not have told you is if you operate on the left-hand side, Vk, oops. Vk dot J there's a different function with the same eigenvalue. So this is called, sometimes I call it adjoint eigenvector, sometimes called left eigenvector. Okay, and this eigenvector is sometimes called the right eigenvector. Okay, so the last little piece that you need to know is that J, actually we don't need to know that. Okay, so what we're going to do is we're going to write delta z of t equals the sum on k of ak vk, ak of t. So we're going to express delta z in a new basis. There's one last thing you need to know, which is vk dagger dot vk equals delta, dot vl equals delta kl equals 1 if k equals l, k equals l, and 0 if k not is not equal to 0. Okay. So all this stuff here is super, super, super important. If you've seen it again, it's going to be completely boring. If you haven't seen it before, sorry, if you've seen it before, it'll be very boring. Otherwise, it'll be kind of new. So just in case it's kind of new, I'm going to go over it again. So, and I assume you know some linear algebra, sorry, or else this will make very little sense. So J is a matrix. It's a square matrix, n by n. And we can take a dot product. So just to be 100% clear, what this means is, so J dot vk, the ith component of this equals the sum on J of J I vk j. Okay. So I assume that you know that, but just in case to be 100% clear. Vk, the jth component of this vector. Okay. So J dot into this vector, if Vk is an eigenvalue, you get the eigenvalue back, or scaled by the eigenvector back, scaled by the eigenvalue. If you're up on the left-hand side, if J is not symmetric, you get adjoint eigenvectors. And these eigenvectors and adjoint vectors can always be chosen to be orthogonal, well, almost always. You get vk dagger dot vl equals delta kl, which is 1 if k equals l. So vk dagger dot vk equals 1 and vk dagger dot vl equals 0 when k is not equal to l. Okay, so those are just math facts from linear algebra. And what we can do, let's write this a little more neatly because it's so important, is to write ak, is to write ak of t vk. So we're just expressing delta z in terms of a different basis. So we haven't done anything. That's just, you can always do that. You can always write delta z as the sum of other vectors. Why not? So now we're going to rewrite this equation using this substitution, and we get d dt of the sum on k of ak of t vk, which we can write as a sum on k of dak dt vk equal j dot the sum on k, let's write it up here, the sum on k of ak of AKVK, which we can write as down here, the sum on K of AK J dot VK, and then plus epsilon G1 of Z naught. Okay, so why is this useful? The first thing that we notice is, well, and this we can write as equals, so the first thing we notice is J dot VK, oops, is that J dot VK is lambda KVK. Okay, so our equation becomes the sum on K of dAK dt times VK equals the sum on K of AK lambda K VK plus epsilon G1 of Z naught. Okay, so what it looks like is we have dAK dt, we have these VKs here that are the same. So we kind of suspect dAK dt equals AK lambda K. We can make this formal, right? So what we're going to do is dot both sides by VL dagger, dots. Dot everything by that. And remember, so I'll put in all the steps, the sum on K of dAK dt VL dagger dot VK equals the sum on K of AK lambda K VL dagger dot VK plus epsilon VL dagger dot G1 of Z naught. Okay. And remember, the super cool thing is this thing is 1 when K equals L and 0 when K is not equal to L. Okay, so that's true of both of these. So in this whole sum on K, only when K equals L does anything survive. And what happens is you get, when you do that, so that means that basically DAL dt is equal to AL lambda L plus epsilon BL dagger dot G1 of Z0. Okay. So we've turned a, so we started with this sort of high dimensional equation. We started with this equation, which is an, n different equations, and we reduce it to one equation, okay, for DAL. And remember, so we'll assume that, I'm gonna write this on the next page because it's so important. So DAL dt equals lambda L AL plus epsilon BL dagger dot G1 of Z naught. Okay. And so remember, so we'll assume it's, we'll assume that Z naught is a stable fixed point. Z naught. Z naught is a stable fixed point. So that means lambda L is less than 0 for all L. Okay, so we can write this as DAL dt equals minus lambda L AL plus epsilon BL dagger dot G1 of Z naught. put absolute value here. Okay. So so if epsilon equals 0, so epsilon equals 0, then AL of t equals AL of 0 e to the minus absolute lambda L t. So you get this decaying exponential. Which is what you expect. If epsilon not equal to 0, you can actually work out the time dependence, but as t goes to infinity, AL equals epsilon VL dagger dot G1 of Z naught divided by absolute lambda L. Okay. So we can write, and so what that means is t goes to infinity, we can write delta Z equals epsilon, the sum on K of AK, which is VK dagger dot G1 of Z naught divided by lambda K. Okay, so it's kind of cool. All we have to do is find the eigenvalues and eigenvectors, eigenvalue and actually adjoint eigenvalue of the matrix J, and then we can write down explicitly solution. And so it's kind of a nice picture. So the picture was that our starting point was some dynamics, Z dot equals G0 of Z naught of Z. And basically we say this has a fixed point at Z naught. So this is Z naught, and a fixed point means no matter where you start the trajectory, you end up here. This is our Z, Z1, Z2, Z3, say. And now if we add in plus G1 of Z with an epsilon here, the fixed point just shifts. So a new fixed point a distance epsilon away. And there's one kind of important thing to notice is we divided by lambda. Okay, oops, I needed to be epsilon lambda K. So we divided by epsilon lambda K. So what we really need is epsilon small compared to all the eigenvalues. So if one of these eigenvalues is really small, which means barely attracting fixed point, epsilon better be 0. Okay, so that's the situation. So okay, so that was a bit of an aside. So remember, the equation we really want to solve is so we started here. So this is okay. I'm gonna actually, what I'm gonna do is gonna tell you what this has to do with our line attractor. So our line attractor is equation is this, right? And what we're gonna do is write this as we're going to find psi naught. So we're going to find psi 0, which depends on this vector r, equals psi of the sum on J of Wi minus J Rj. Okay. And psi 1 of R equals psi of the sum on J of Wi minus J Rj plus epsilon, the sum on J of Vij Rj plus epsilon Hi minus psi naught of R. Okay. Okay, so we basically, and that what this means is tau dri dt equals psi 0 of well, I'm going to actually write it as vectors. So in vector notation, we can write tau dr dt equals psi 0 of r plus psi 1 of r. Okay. And we put the epsilon inside here, but as epsilon goes to 0, psi 1 goes to 0. So for small epsilon, psi 1 is proportional to, so psi 1 is actually proportional to epsilon. Actually, let's put an epsilon here in the definition. So, okay. So we'll actually make it really crystal clear, okay? And we can see, so as epsilon goes to 0, so psi 1 is really this whole difference divided by epsilon. And as epsilon goes to 0, that's got a nice, we can Taylor expand, that's got a nice limit, okay? So this equation here is very similar. Actually, we have to, let's be a little more careful here. This is actually a vector. And the ith component of this, so the ith component of this is this quantity here, okay? And the same thing happens here. This is actually a vector, okay? And its ith component is also a vector, the ith component. Okay. But in the end, it gives us this equation. Okay. And that equation should look very much like this equation. Okay. It's basically the same equation. We're going to use the same techniques. The only problem is one of our eigenvalues is going to be 0. Okay. Okay, so let me take a break for 5 minutes. As usual, I'll be around if you have any questions. If not, come back in 5 minutes and we'll finish off. We'll actually do the analysis and find out what we get. Okay. Okay, gang, I'm back. As usual, we have to delete these, stop sharing and start over. So hopefully, share content, whiteboard. Hopefully, so you're going to see in some sense very similar analysis to before. There's a twist that's kind of important. So where are we? We are at set of equations look like this. The tau dr dt equals psi 0 of r. Minus r, remember? Hopefully I include that. I may have forgotten the minus r term in the previous slides, psi 1 of r, okay? And we know that f of theta is a fixed point at the 0th order dynamics, equals psi 0 of f of r. Sorry, f of psi 0 of f of theta, okay? In components, this is fi of theta equals psi of the sum on j of w I minus j f j of theta. Okay, and that's just a point somewhere on our line attractor, which is parameters by theta. Okay. Okay. And we want to do, and so we're going to do the exact same thing we did in for a point attractor. We're going to let r equals f of theta plus delta r. Okay. And actually f of theta not. Pick some value of theta, so some point on the line attractor. Why does that happen? Our line attractor looks like this. So this would be, say, theta naught. So we're perturbing around some point in the line attractor, and we want to know the effect of this extra term here. Okay, so we're going to write down an equation for delta r, do the exact same thing we did before. Tau d delta r dt equals psi naught of r plus delta r minus r plus delta r. Okay, sorry. So f of theta naught plus delta r minus f of theta naught plus delta r plus epsilon psi 1 of f of theta naught plus delta r. We'll do the same thing we did before. We're going to ignore this term because of the epsilon. Ignore that term. We're going to Taylor expand this term. And I'm going to actually Taylor expand. So this term is partial of psi naught. So this is psi naught of f of theta naught plus the partial of psi naught with respect to f dot delta r. Okay, and I'm going to call this j. So it's a little different than before because j, well, you'll see in a second. And so jij, j is a matrix, and jij equals partial of psi of the sum on k of w I minus k f k of theta naught with respect to fi of theta naught. Okay. And when we do that, we get tau d delta r dt equals, we have a psi naught of f, just write f, I write f of theta naught, plus j dot delta r. J depends on theta naught, but I can suppress that. So we're going to put approximately equal to minus f of theta naught minus delta r plus epsilon psi 1 of f of theta naught. This should be, okay. So this is our equation. And because f of theta naught is a fixed point, these terms cancel. Okay. And we can write this as tau d delta r dt equals j minus the identity dot delta r plus epsilon g1 of f of theta naught. And this is no longer g, this is a psi. Okay. So that's the equation we want to solve. And so it helps to think about what's really going on in terms of our attractor space. Okay. So a picture like this. This is our line attractor. So every point along here is f of theta. So this point here is f of theta naught. Okay. And what's really important is moving along the attractor. So this direction here, this is df of theta naught, d theta naught. Okay. And one way to think, the way to think about that is if you had, it's really, that's actually an important point. So I'm going to draw it over here. So here's our line attractor. And let's say you had this point here was f of theta naught. And this nearby point was f of theta naught plus delta theta. Okay. And basically these are linked by a vector. And that vector, if theta naught is small, this little green vector, which is hard to see, points along the line attractor. Okay. And so f to the green arrow is equal to f of theta naught plus delta theta minus f of theta naught. And that's approximately equal to delta theta df d theta naught. Okay. So this direction, df d theta naught, really is this direction along this line attractor. Okay. So what we really want to know is the component of delta r that lives in this direction. So what we'd really like to write is what we want to do. So what we want to do is write delta r equals f prime of theta naught delta theta. Okay. We care about the component of delta R that points along the line attractor, because it's really moving along the line attractor we care about. We don't really, oops, shoot. Okay. So we care about moving along the line attractor. We don't care about movement away from the line attractor. However, I mean, this is why it gets kind of hard. So if we wrote delta R equals F, so that F prime, this is a particular vector in particular direction, there's no guarantee it's going to line up with the right-hand side, which is also a vector. Okay. So what we're going to do is say, okay, we're going to do pretty much what we did before, plus the sum on K of AK, VK. Okay. And the VK are the eigenvectors of J. So J dot VK equals lambda K. I'm going to put a minus sign in here. Lambda K VK. So these are eigenvectors of our linearized dynamics of Jacobian, and they should all be negative because, or negative or zero, because this is a fixed point. Okay. So that's actually. Remember, this is the identity matrix. Identity matrix. So I delta R equals delta R. Okay. Okay, so this has been kind of non-trivial, so let me go over it again. Back up a slide. So we started with, so this is what we derived last time, that we're going to basically, when we perturb our function, we perturb it by this, and epsilon was basically, it's probably worth, well, epsilon is it's probably worth writing down. Just to remind you what it is. So we'll do it in sort of do it in vector notation. So psi 1 equals psi naught. Actually, all right. Kind of abuse notation here. Psi naught, or psi of W, our unperturbed matrix dot R plus epsilon V dot R plus epsilon, I think I called it H, minus psi of W dot R. And all this got divided by epsilon. Okay. So it's a difference between our perturbed function, our unperturbed function divided by epsilon. As epsilon goes to zero, this has a well-behaved limit. Okay. So this is our equation. So this is the equation we want to solve. And we solved it by letting R be close to the line attractor, but perturbed by a little bit. We did the usual thing, Taylor expanded here, the first order, ignored that because epsilon is already small. We got that, we got an equation that looked like this. So the dynamics of the perturbation, you get some linear terms and then the forcing term for the extra function. And what we care about is position along the attractor, okay? And we would like to just say, oh, delta R is really points along the attractor, but it points in other directions as well. And as usual, we'll just let it be the sum of the eigenvectors, and these VKs are, actually, I'm going to put, I'm not going to put a minus sign here. These are these VKs are the eigenvectors of the J. Okay, so kind of pretty non-trivial. Okay. Now, one thing that to note that's kind of important is that delta R. So it turns out that J minus I dot F prime is zero. So this, well, We'll come back to that in a second. Okay, so what we're going to do is write so we, given we're writing delta R like this, we can now write down our equation for delta R. So d dt, so we have f prime of theta naught times theta dot, or delta theta dot, the thing we really care about, plus the sum on k of ak dot vk equals j minus I dot the sum on k of vk. Sorry. AK vk plus epsilon psi 1 of f theta naught. Okay. And so this term here, this is equal to, so j dot vk is lambda k. So this is sum on k of lambda k minus 1. Oh, actually, I forgot a term. AK vk. We forgot a term here. Very important term. J minus I dot f prime of theta naught times delta theta. Okay, so that term goes in here that I forgot. Okay, so we can write this as j minus I dot f prime of theta naught delta theta plus epsilon psi 1 of f of theta naught. Okay. So here's the cool thing. This term turns out to be 0. Oh man, did I? Not good. This term here turns out to be 0. And the way that we can see that is, remember that f of theta naught plus delta theta equals psi of, or psi naught of f theta naught plus delta theta. Let delta theta be super small and we'll Taylor expand. So this is f of theta naught plus f prime of theta naught delta theta equals psi naught of f of theta naught plus f prime of theta naught delta theta. So we should put approximately equal to, but I'm gonna let delta theta go to 0. And this is approximately equal to psi naught of f of theta naught plus this is d psi naught df of theta naught dot f prime of theta naught delta theta. Okay, and this, you remember, is just a Jacobian. So what do we have? We have this term cancels with this term, and that tells us that f prime of theta naught delta theta equals j dot f prime of theta naught delta theta. And we will cancel the delta thetas. And that tells us then that j minus I dot f prime theta naught equals 0. It also tells us that f prime of theta naught, so it also tells us that f prime theta naught or j dot f prime of theta naught equals f prime of theta naught. So this is an eigenvector of j. Okay. So this is super, super important, right? Because it means that this term goes away. And our equation means two things. One goes away, and our equation becomes f prime of theta naught delta theta dot plus the sum on k of ak dot bk. So dot, I don't know if I said that. So this is equal to d delta theta dt. Standard notation, at least if you grew up in America. I assume you know this, but I'm not really sure. But just remember that dots mean time derivatives, equals the sum on k of lambda k minus 1 ak vk plus epsilon psi 1 of f of theta naught. Let me see, did I do that right? Yeah. Okay. So what do? We multiply by adjoint eigenvectors. So multiply by v0 dagger, which obeys v0 dagger dot j equals v0 dagger. Okay. So just like f prime was the eigenvector of j, v0 dagger is the adjoint eigenvector, and that implies that v0 dagger dot bk equals 0. Okay, that's orthogonality, and when all is said and done, we get that delta theta or d delta theta. There's a tau here. Tau multiplies all this. I have tau on the previous page. No. Put that there. So tau d delta theta dt equals v0 dagger dot or epsilon psi 1 of f theta naught over v0 dagger dot f prime of theta naught. Okay. So and so remember that basically we had theta equals theta naught plus delta theta. So we can just write this as, so theta naught's arbitrary, so we can write this as tau d theta dt equals epsilon v0 dagger dot psi 1 of f of theta naught over v0 dagger dot f prime of theta naught. Okay. So it's a super cool result. So we just need to calculate eigenvectors and eigenvalues, and we can compute everything. We can know how fast it moves along the line attractor. I'm not totally sure. So whether or not you think the math is important depends quite a lot on what you want to do with your life. It's always good to be an expert in linear algebra, so hopefully that was useful. But we can actually take away, actually, hold on. There's a mistake here. Okay. So given its derivation, we can sort of, we come to a kind of a non-obvious conclusion. Wasn't obvious from anything we've seen so far. So if we start with, So this epsilon equals 0. So we start with a line attractor. So this is epsilon equals 0. Okay, so this is a true line attractor. Okay, and this, remember, it's parameterized by theta. Because it's a true line attractor, if you start here, you stay here forever. Okay, but once we add in finite theta, finite epsilon, all of a sudden we start drifting. So finite epsilon causes drift along the attractor. And it doesn't matter how small it is or what perturbation it is, it causes drift. So this function, we can think of this as just, some function of theta. So it's 1D dynamics, and g of theta is generically non-zero. Right? Having g of theta 0 everywhere is very unusual. It's a very unusual function. If you chose an arbitrary function from a function space, it wouldn't have this property. And you can have fixed points. You can have g of theta can be positive for all theta if it's periodic. All sorts of things can happen. But the point is that you get drift. So, so unlike point attractors, if you go back to original analysis of point attractors, what we found was a small perturbation to the function move the point by order epsilon. This is not the case for line attractors. Line attractors are structurally unstable. Unstable, so they don't really exist. Okay. So why do we study them? So this is where it's kind of important. So let's back up and think about neurons. So remember neurons, back to our equation that seems to be my favorite equation because I write it down all the time. So neurons, so tau dv dt, let's say the voltage. I mean, I barely need to write down the whole equation. Plus the sum on j of w I j tj of t. So none of this is important. What's important is that tau is on the order of 10 milliseconds. Okay. So neurons have very fast dynamics, equals 1/100th of a second. Okay. So neurons, within a second, they've forgotten everything. So if you have a line attractor, so drift along the line attractor. So what's really important about line attractors is that, so drift along the line attractor. The line attractor can be slow. Okay, it scales with epsilon. It scales with what's epsilon is. Let's go over here. Where did we write down? Here. So it scales with epsilon. It scales with how much you perturb your function around this thing, and epsilon can be small, and so you get slow drifts. And so slow drift along a line attractor can be super useful. You can use it to remember things. You can use it to integrate evidence. If you're sort of getting noisy information, you might want to integrate it to find out. We'll see that in decision making. If point on line attractor corresponded to position of your eyes as you move your head, you might want your eyes to move slowly. And certainly on time scales much faster than the time scale of neurons, which is 10 milliseconds, okay? So even though line attractors don't exist, the fact that, so what's, the key feature of this is that, so there's sort of two things going on. One is, so although the line attractors don't drift, there's rapid relaxation onto the line attractor. Okay. And then once you're on a line, there's slow drift. Okay, so if the line attractor has meaning, you can actually use that slow drift for computations. And when I talk about decision making, I had to come back to this because in decision making, we often get noisy evidence over time which we have to accumulate. Instantaneous information may not be very large. Okay, so I'm going to actually end with a little intuition about what happens. So we have this somewhat abstract equation, and I'm going to actually tell you what it means in terms of our picture of a bump. Okay, so remember, one of our ways of thinking about line attractors, if this is Ri star, it's a hill of activity which consists of a bunch of points. So these are really a bunch of points, but I'm not going to draw them. And so this is really, so we can write tau Ri star dri star dt equals f of sum on j of w I minus j rj star plus, actually I don't want a star there. I'm going to add some external input, which could come from any source, minus Ri. And now we can kind of see what kind of external input. So it turns out that theta dot, in this case, theta dot is proportional to the sum on I of fi prime hi. Okay. As we're going to see, this makes a lot of sense. So suppose hi, so we can take a couple examples. One is that, so what if hi equals a constant? So what does that do? Basically, it takes every neuron and hi constant, it basically, Ri dot, so remember Ri is I should get rid of the star. Hi constant, so if this is a constant, every neuron sort of gets pushed up by a little bit, right? That's all that happens. Every neuron getting pushed up by a little bit doesn't move the bump anywhere. And in fact, that's consistent with this. So what's fi prime? That's how much as theta moves, the firing rate changes. If this curve shifts to the right, so let's say if the curve shifts to the right, a rightward shift causes, so a rightward shift, which is an increase in theta, theta increases, causes a decrease in firing rate. Because a decrease in firing rate over here, it causes an increase in firing rate over here. So if we plotted fi prime, it would have the shape of, so fi prime is actually negative, 0, and positive here. So this is fi prime of theta. okay? And it's basically an odd function. So if you sum an odd function, so if you sum it, so hi equals constant, sum on I of fi prime h is 0. Okay, so basically hi constant, if all you do is move up everything equally, then nothing happens. Theta dot 0. On the other hand, if you say hi prime, so what you really want is hi prime, so hi proportional to fi prime. In that case, now, for that case, so hi proportional to fi prime, the sum on I of fi prime, hi proportional to sum on I of fi prime squared, and that's big, okay? So you really want hi pushing up in the front of the hill and down on the back of the hill. And that moves it. If you want to go the other direction, you push up in the back of the hill and down in the front of the hill. Yeah. So if you push up here and down here, you move to the right. You push up here and down here, you move to the left. Now, having an input, so this is kind of, if you want to move the hill, having an input like that is nice, but that input has to know all about the firing rates. So it turns out, I'll leave you with one last point. If hi equals the sum on j of vij, put epsilon in here, rj, and vij is odd. So vij equals, first of all, it's nice if it's actually, if it's vi minus j equals minus vj minus I. So odd function. In that case, it's not that hard to show that that implies the sum on I of fi prime vi minus j fj is big. Okay. And so it's nice. So if you can put in, the extra term you add is this term, this odd function multiplying by the r's, you can actually move the line attractor. And if you set epsilon either to positive or negative, the amount it moves is proportional to epsilon. So remember, as always, that theta dot, I'll put an epsilon in here. Has an epsilon in here, right? Well, actually, there's no epsilon because, but usually hi is proportional to epsilon. In the case where hi is proportional to epsilon, theta dot is proportional to epsilon, and you can make epsilon positive or negative and move the bump in either direction. Okay. So actually, I'll say one last thing. You can obviously have higher dimensional attractors. You can have bump attractors. The bump attractors in 2D. So I'm going to draw contour plots. These are bumps. And you can move these around, again, using the same way. So these are bumps, and these actually been observed. These are place cells in hippocampus. And sometimes the place cells are periodic in the case of grid cells, which there was a Nobel Prize. Why, I'm not sure. But you can have, in principle, you can have 3D attractors, although none have ever been observed in the brain. But it might be quite nice, right? If you want to remember color, it's RGB, it's 3 numbers, although it can be sort of reduced to 2. Okay, so so sort of the bottom line is we've chosen a particular set of weights that allowed us to have, instead of point attractors, line attractors or higher dimensional attractors, but they're structurally unstable, which means they don't really exist. On the other hand, what's really true is they kind of exist. So the key thing to keep in mind is this picture. There's rapid relaxation onto the attractor and slow drift along the attractor. Some of the drifts you're stuck with from noise, and some of it you might control to actually force you to move along the attractor. Okay, I'll end here and I'll stay on for 5 minutes if you have any questions, and I will put this on the website as usual. And next time we'll start talking about deep networks.